Daniel, I invite you to the stage.
Hello. Okay, that one works. Hello? Cool. All right. Fantastic. Welcome everyone. And if you can hear me out in the rest of the conference, make your way down to the trade stage, so you can see what Curvecrete is all about. So I've got the clock on there as well, 9.5 minutes, so we better keep to time. All right, so my name's Daniel. I'm an architectural engineer, a lecturer at Swinburne University, and a co-founder of Curvecrete. Now, Curvecrete is a company that is focusing on deleting these two numbers to 0. I'm sure we're all on the same page there, with reducing our 8% global emissions due to concrete and the 40% of Australia's waste that is contributed to by construction and deconstruction. So how we do that is through the power of curvature. Curvecrete can eliminate 50% of the material mass with the curves that we produce. The curvature that I'm talking about here, if I had a third hand, I'd be able to hand this one around. Thank you. The Opera House puts Australia on the Architectural International map. And this was built in the 70s, but I don't see another innovative, really extreme example of curvature in Australia since this time. So I asked the question, why? We have all of this technology available, why haven't we built anything since? Well, it's because it's really complex to build. We think we've figured it out. So we've developed a robotic system that is an adaptive mold. It's a ruled surface system, so that panel that's coming around now, you'll be able to run your eye down one edge of the panel, and you'll see that you actually get straight lines. And you can do that in the other direction as well. So these straight lines that make up the curvature has a twist. So it's called a ruled surface. We'll pass another one around. There we go. And that ruled surface is one of the stiffest shapes or geometries in nature. So relative to a flat panel, we can, for a subtle curvature of about 20-meter radius, I'm going to skip ahead a little bit. At a 20-meter radius, we can increase the stiffness by an order of magnitude. So rather than it deflecting 10 millimeters, it will deflect only 1. For flexurally dependent applications, like noise walls or like facade systems, potentially, we can reduce the amount of material significantly. So we don't just manufacture molds and the curved panels. We're also a design consultancy full of architectural engineers and architects that also make stuff. So we're looking at ways in which we can work with everyone here to develop construction systems that are more efficient, not just in how we produce them or the mass reduction potential of them, but how we install and disassemble at the end of life. So I want to pass around a couple more examples of that. This is more or less how we do it. Robots and a team, we produce curves. I've brought with me a part of our robotic system. We utilize all sorts of different advanced manufacturing techniques. This component was 3D printed in one go. So there's 3 parts to it that rotate around a central point. That makes the mathematics of the robotic system quite simple. So this makes up 4 points of the robotic system to create the ruled surface. And it's probably perplexing as it is by itself, but I welcome you all to my factory in West Footscray. You can check out the robotic system. You can connect with me on LinkedIn and set up a time to come in. We bring in groups all the time. So I'll pass this one around as well. So this component was previously made up of about 40 different parts. And through, I don't know how many, probably like 80 iterations or something, we got it down to a point where we can just print it and then reinforce it with some bolts. This comes from a background of looking at how we can mass reduce connections. So utilizing the robotic system there where it can move, we also take that knowledge and try and design things that don't move, because we want our buildings to stand up. This in my hand is a structurally optimal connection. It's a bolted connection that is 10% of the mass of a standard connection, within a stadium, you need about 20% of the mass that would go towards bolted connections. So if you can reduce the mass of the connection itself, you can save a lot of material and save cost through utilizing a bolted connection system. So from that process, we're okay. So the challenge around this connection is that it's 3D printed. It might be a bit slow to produce, and it's hard to make it comply for a construction project. So I'll pass this one around. So that is like the most mass reduced that we could go. And then this connection here uses plate elements that are laser cut, but then it creates stiffness through curvature once again with curved or doubly curved plate elements. So we're working with an integrated design approach to try and utilize the latest manufacturing technique to reduce the amount of material all the time. Now we get to this last connection that I want to pass around as well, which is a precast coupler that is used with our structural precast systems. And it's one that can be utilized in a system where it can be disassembled at the end of its life. So the assembly and disassembly is quite efficient. So those two portions on the side get cast in, and again, at our factory you'll be able to appreciate a little bit more. So we're a growing team. So this is the startup or the business side of what we're doing. We have designers, material scientists, and production teams. We have a factory facility. It's 500 square meter facility in West Footscray. We've completed our first project, which was a spiral staircase that we completed last year. It's for a multi-residential building in Melbourne. Again, if you're interested to come and visit this, I can organize a tour for you to check it out. This consists of about 35 panels that we produced all in the same robotic system, and every one of the panels is different. We developed a meeting pod system, which is a prototype for a curtain wall system, completely integrated tensile cable net structure, which allows the panels to be clamped in to create any curved shape on the facade. So there's no secondary steel. We're designers that have won multiple awards for Environmental Solution of the Year, for instance, and recently Engineers of the Year in Victoria, which is pretty cool. Total surprise. But yeah, now we're working on much larger projects So we've got a facade job in Hawthorne East, which we'll utilize our low carbon material on. Our precast disassemblable planters that we've developed for the Austin Hospital, which is currently under production. And what's destined for us is that over the next 12 months we're going to increase our factory space capability in terms of how we deliver on infrastructure projects. So we're building much larger robotic systems that are going to be on the order of 10 by 5 meter in order to deliver on noise walls. We're looking at earth retaining structures as well. Recently did an investigation in noise wall application where we're able to reduce the mass of the material by 50%. It's been verified by Arab engineers, and now we're going to detailed design phase for that. Come and see us in stand 44 if you'd like to connect with us. And love to know if you have any questions. Some of the applications that we can potentially build together. So thank you very much.
Thank you, Daniel. For our next presentation, I introduce to the stage